Okay, off we go. So here's where we were last time. So I hope everybody had a good break and got some relaxation in. I hope you didn't forget too much math. It's a unfortunate but natural phenomenon. So just as a quick reminder, here's what we were talking about last time. We were talking about this idea of generalizing the idea of a Riemann sum. Initially we had only talked about, in your Calc 1 classes, you talked about Riemann sums for one-dimensional intervals. Then a couple weeks ago we started talking about doing the same kind of thing, chop it up, add it up, for accumulating quantities for a two-dimensional domain. And then last time we talked about what that would look like for a three-dimensional domain. And again, the big idea is if you're trying to compute the grand total amount of, let's say, mass, but any accumulating quantity, but I like to think about mass, you can chop it up into little pieces. The whole is the sum of the parts. And on each little piece, whatever the quantity is, on that little piece, if it is an accumulating quantity, then how much of that there is in that piece should be quantity per unit volume times volume. Because this little box's size is described by its volume. Okay. All right. So, definition, notation, et cetera, this is all repeating, so I'm not going to go through all the details again. Initial example, we've already done. Let me remind you at this point, this is another really huge one, how you think about this in your mind. If you want to avoid the, very easy confusion that comes up with so many students, right? It's important to consciously, right, make a deliberate effort to organize in your mind how you think about the various different pictures that we draw for various different kinds of integrals. So you can see on the left over here we have, a lot of people like to think of single variable integrals as area of the curve. It's very comforting for various reasons, some good, some bad. Volume under a surface for double integrals, etc. Well, there are also these other points of view. You can think about a single variable integral in terms of the accumulation of mass, or anything, any accumulating quantity, over an interval, one-dimensional picture. There's no two-dimensional picture here. No need for a two-dimensional picture. Chop it up, add it up. That's what this is. End of story. There is no area. Right? And then likewise, for a double integral, you can think of it as representing an accumulation over a two-dimensional region. Double integral, two-dimensional region, 2, 2. No need for 3 dimensions. Right? Doesn't come up. Not relevant. So you have these competing sort of points of view, and they all have their merits. But as I emphasized last time, you really have to take this point of view here if you want to make sense out of a triple integral, because that's the only one that extends. I suppose you can insist on thinking about single variable integrals this way and double integrals this way. I guess I'm going to put a on that. But you cannot do that for a triple integral. Right, so make sure you're not trying to set up false analogies. I get asked so many times, so let's just try to head it off at the pass. Why is it that a double integral looks like this and a triple integral looks like that? They're both three-dimensional pictures. What gives? Well, this is what's going on. You're comparing apples and oranges. Okay, all right, we talked about all that last time. Okay, so moving along. Now there's some formalities that we're going to have to run through pretty quickly for a combination of reasons, not least of which is we kind of can't do some of the arguments that we did with double integrals. They're intrinsically four-dimensional arguments. We just can't draw those pictures, and this is not a good use of our time. So what I'm going to point out, though, is that we can still have a strategic diagram that's basically the same as what we did for double integrals. Now, what we can't do, as we just discussed, there is no sort of analog of volume like there was for double integrals, because that would be four-dimensional. I don't know what to do with that. Right? So now, since there is no analog of volume, I also can't really, in this context, relate this to iterated integrals because I don't even know how to talk about it in the first place, right? And I can't relate it to a summation because, again, I don't know how to talk about that in the first place. So a lot of this doesn't work. And obviously, I can't make any sense out of that either, right? And I claim that, again, there is no immediate connection between some application and an iterated triple integral that I might write down for some reason. It's not clear how that argument would go, and you'd have square peg round hole problems. So that's what you can't do, right? But I'm going to claim, without proof, and I hope you're willing to buy into this. And this can be proved. It's just that it's going to be algebraic and formal and not something that we really need to get into. But triple integrals can be computed as iterated integrals. So this still works. I can't justify it for you. But it's still true. And I think it's highly believable. You can almost, this is a little sketchy. Don't write this down, but it's almost like you can see the DV developing there, right? So those little issues that I'm sweeping under the rug and I don't want to go into. So hopefully y'all will find that believable, right? And so when we have, as we do, we've already talked about how we can take, we took a mass application question and we turned it into a triple integral. So we've got this connection here. And I just asserted, and hopefully you buy it, that there's a connection here. And of course, cranking out the fundamental theorem is something we can always do. Once you have iterated integrals, those are single variable integrals sort of nested inside of each other. So you can crank them out, starting from the inside, moving to the outside. So we have a strategy. We have a path to victory here, right? That's how we're going to do all these triple integral problems we're about to see. I just can't make some of these arguments. Everybody okay with that? Everybody happy? Okay. All right. Okay. Let's see. Let me erase the. Okay. There we go. All right, so just to be explicit, by the way, and I'm just mostly going to let y'all read the following, but how do we use the fundamental theorem to crank out a triple iterated integral? Well, it's just like with a double integral, just, more so. So again, if you want to compute the whole as the sum of the parts for mass, again, we already motivated that this is how you would compute mass over a three-dimensional region. Whole is the sum of the parts, and mass per unit volume times volume gives you masses, right? So this is the argument we made last time. I am claiming, as we just claimed, that you can turn triple integrals into iterated integrals. And now it's just a matter of cranking it out. Again, we start with the inside integral. This is my calculation for that inside interval. Notice the variables further to the outside are to be treated as constants. So again, easy mistake to make, but that xy right there. Oh man, at a quick glance you're thinking, wow, I've got a product of three functions and I'm going to have to do some probably integration by parts or something like that. Very easy to sort of get, to fool yourself into believing that it's harder than it is. But this is just a constant times 2z. And of course the antiderivative with respect to z being my variable, the antiderivative of 2z is z squared, and the constant just comes along for the ride. Right? Everybody happy? Okay, so careful about that. Yada 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 for the rest of these steps. Right? So you notice we do the inside integral, during which the outside variables are treated as constants, and then you just keep on going inside to outside. Okay, check through these details. Make sure you can follow along, right? Always good, yes?
Is the ordering of
Yeah, in this example, this was an arbitrary choice, and we're going to spend a bunch of time in a few minutes talking about how to make good choices. Yeah, right. Yeah, in this case, it kind of doesn't matter. Okay, so what do you do with non-rectangular domains? This is another one of these things where I can't really give you the same argument that we did for double integrals. This is a healthy exercise to look back in the notes. How did I argue for double integrals that that for non-rectangular domains, the only thing that matters is the inside bounds? And how did I make that argument? And I made it by making a volume argument. By going to that, the graph point of view, this dimensionally inaccessible point of view at this point. So again, I can't give you the argument. I can't draw the pictures. They would be four-dimensional pictures, right? But the punchline is exactly analogous. So let me just walk through a point of view on what that analogy is. This is, I guess that's a pretty good, okay. So this is our process. It's a little bit too big. Okay, here we go. So first thing we do is we have to make a decision about what order to do the differentials. Now, just to get the ball rolling, just to have an example where I can draw pictures, I'm going to do this order here. No reason, right? This is an arbitrary choice. But let's suppose that I'm doing it like this. And remembering that we always slice outside to in. So we're going to start off doing X slicing and slicing perpendicular to the X-axis. There's the X-axis. There's a slice perpendicular to the X-axis. Now three-dimensional instead of two-dimensional, right? So the picture is harder to draw. This is what a slice looks like. Right? And let's see. Now I've got to decide on where are the first and last of such slices. I think it's a pretty easy pitch in the case of this lump that I've drawn here, that for that first slice, we're going to have just kind of this point back here. That's where your vertical slices kind of first touch the solid here. Okay. And then the last slice is, I'll use a different color. The last slice is going to be, this sort of front little point. That's where, again, as I'm slicing, that's the last one that touches it all. Everything else is a swing and a miss. Okay. All right, so you can see that from the picture. Depending on the geometry of the picture, you can figure out where these points are. You can solve for these bounds, whatever they end up being. There you go. Okay. And then, just like we did for double integrals, once we found the bounds, right, we slice orthogonal to the differential axis, we identify the bounds, then we're going to fix a slice, specifically a generic slice, and then we're going to move on to the next variable. That's exactly what we did with double integrals, and the analogy works very nicely. So again, let's see, a generic value of x gives me a slice that looks something like this. We're going to fix that. All of our attention, as we go through and do the y slicing and the z slicing, all of our attention is going to be on that one x slice. And then, now this is constantly confusing to some students. Students say, okay, wait a minute, as I look at my y values, shouldn't I worry about stuff over here? Right? Don't worry, we'll get that. We will get these points. Just not for that value of x. We'll get these points for some other value of x. Right? That they're not on the appropriate x slice, then they're not relevant to our dy and dz computation of what's going on that x slice. Okay. All right. So let's see here. We have our x bounds. Our x bounds are that. We fix a value of x. And now we're going to go on to our y slices. What's the range of values for y? Well, here's what y slices look like. Right, now again, you got to use your geometric imagination. This is what the slices look like when you take slices perpendicular to the y-axis of, again, of our x slice that we've already done perpendicular to the x-axis. So this, geometrically, again, kind of challenging. This picture took me a long time to draw. Non-trivial geometry and non-trivial art. So anyway, slice of a slice is going to be a bunch of little line segments. Okay, so with that noted, first slice going to be there. There will be some corresponding y coordinate. That's going to be our lower bound. And now notice, and this is really important, back up to our little generic picture here, where that bound is comes from where that point is, and that point, its location depends on which x slice are we looking at. Right? Different x slices will give me different points, which will give me different y lower bounds. So because it depends on x, it depends on the variable further to the outside, it is a function of that variable further to the outside. Just like with double integrals. Everybody happy?
The last part of the function.
Yeah, well, that's right, because it depends on x, right? I mean, you take different values of x, you're going to get different x slices. They're going to be totally different shapes. They're going to be in different places. And so the leftmost point will be different depending on what x is. Yeah, right. Okay, likewise the upper bound. Everybody happy? But by the way, many examples to come. Okay. Yeah?
Does where XYZ matter?
It matters very much, absolutely. In this example, it's totally arbitrary because this is just a generic lump, right? We're not getting into specifics. But yeah, it absolutely matters a great deal. And we'll talk about pros and cons and considerations in a few minutes. Yeah. Okay. All right. Okay, so now let's think about as we move on, we're gonna, so we've already, let's see, I lost my, okay, yeah, so we've already fixed an x. We were focused on this x slice, and now we're fixing a y. We're looking at a particular y slice of our x slice. Now let me redraw this picture a little bit. We have fixed x and y. Right? X and y are now both fixed. Think of those chosen values of x and y as representing, I like to think of it as a point down here in the xy plane. We are restricting our attention now just to that y slice of our x slice. And then on that, we can ask, again, the same question we keep, sort of we're cycling through this process up here. We can ask, all right, what does it look like when I take z slices of our y slice of our x slice? Right, so looking at this little blue interval here, this moving up this little blue line segment, that's how we do our z slicing. And again, I can see right here on the picture that there's going to be a first value of z. That'll be our lower bound. It's, of course, going to depend on x and y because it depends on where that point is. So this is a function of x and y. Again, function of the variables further to the outside. And then likewise the upper bound. All right. Is everybody on board? All right. So that's the plan. This is geometrically kind of, now of course this is generic. This is just a made up schematic, right? This is not a specific example, but that's pretty much how this stuff's going to go down. So remember, the bounds are always functions of the variables further to the outside than whatever variable you're looking at. And for the purposes of the integral, as you do the integral, those variables further to the outside than the variable you're looking at are to be treated as constants. Okay, so let's do one. Oh, well, real quick, generic advice. This is all very generic. When you construct the integral, it's always outside to inside. I mean, that's how we did our slicing process. We've already commented on this. Bounds are functions of the outside variables, whatever's further to the outside. And then this other sort of generic observation we've made with double integrals. If you want to know a given bound, it comes from looking at certain points that you can identify in your picture. Those points will be on various surfaces, possibly a surface, possibly several surfaces. Those surfaces will have equations, and then you can just solve for whatever variable you need. Okay, so let's do an example. First example, pretty classic first example. I like this example because it gets rid of all the nasty algebra that can come up. So there's no quadratics, there's no fractions. This is all just glass smooth convenience. But the focus here is on the process, not the answer. Okay. So we've got this tetrahedron. We've got 3 coordinate planes. Right, so there's this coordinate plane is y equals 0, this is x equals 0, and this is z equals 0. And then we also have this plane, which I like to draw like this. And you can check those intercepts to confirm. And that makes a tetrahedron, as I have drawn here. Is everybody on board with that picture? By the way, you may have noticed, I've already kind of commented, and I'm going to comment on this several more times. The geometry here is no kidding. Right? This is geometrically challenged. That is the nature of the material. Don't think of this as a geometric alternative to what you could do by some algebraic method. That's basically non-existent. Right? This is intrinsically geometric. So as such, you basically have to have a picture. Now, if you can do it in your head, that's one thing, but I'll point out, first of all, that means that you have a picture in your head. So that is not a counterexample. You have to have a picture. And then secondly, keep in mind, one of your responsibilities as a student, right, is to communicate your thought process. And again, you're thinking about it geometrically. You've got to communicate those thoughts, and the way we do that is with a picture. So the picture is, it's just, if you want partial credit, if you want me to believe that the reasoning that you're asserting that got you to the answer you got, this is what's going to make me believe that you understand how to do it. So make sure to draw a picture. While we're at it, let me also point out, for those students who say, I'm no good at drawing pictures. Okay, well, we got to get good at it. Right? Now, I think there's 2 things that will help. One is I do have some videos on my YouTube channel. They're in the miscellaneous topics playlist. It's everything that I know about how to do mathematical drawing. It's about an hour of me talking about mathematical drawing and doing examples, carefully, gory detail, meticulously, every single aspect of every drawing that I make. I explain why I'm doing, drawing it that way. I think you'll find that useful if you're not already good at this kind of thing, so I encourage you to watch that. Obviously, you don't have to. I hope it might be helpful. The other thing that's very helpful for mathematical drawing, practice. It's one thing to know what you should, in theory, do. It's another thing to make your mechanics of your hand actually do what you want it to do, right? And again, you're going to need to do this on exams. So it's just unavoidable, right? So practice is going to be essential. Okay, so let's go through the process, starting now fairly arbitrarily in this case, and I'll talk about pros and cons of different slicing orders in a few minutes. But let's arbitrarily get the ball rolling with this right here. We're doing X slicing first. There's the X-axis. Here's what a slice looks like perpendicular to the X-axis. All right, let's think about first and last. The first slice is right there, where X is obviously 0. And again, sometimes the fish just jump in the boat. You get some freebies, go for it. Everybody happy with that? Okay. What about the last slice? And that's going to be this point. And now again, your intuition for the geometry might be good enough that you can just kind of look at this and see what the X coordinate is at that point. But again, let's focus on the process. It's not about the answer. Let's think process. What geometrically can I say about this point? And this is the point I want to understand. What do I know about it? So as we discussed earlier, that's going to be on various surfaces. Write down what surfaces that is on. For example, this right here, it's on that face of our tetrahedron. That has that equation. But wait a second, now that's not all. It is also on, color choices, this face, which has that equation. And that's not all. It is also on this face, which has that equation. And that is all I know about that point, right? And keeping in mind, I'm trying to figure out what my upper bound is for the X slicing. Thus, I'm trying to understand that point. And these are the 3 pieces of information that I know about it. So, again, how do we proceed? Well, bounds are determined by points, which are on certain geometric objects, in this case surfaces, which have certain equations, following our usual process here. Right? And then what do? Well, we solve for what we're interested in. Again, I'm superstitious. I am easily mentally derailed sometimes. I get off track. I get confused. So my little superstition for myself is always go back and visually remind myself, wait a minute, what is it that I need to solve for here? Right? So I need to solve for X because I'm looking for X bounds. And so in this little system of equations here, I'm going to solve for X. And it's allowed to be a function of Y and Z. If it were to have turned out that the formula for X had Y's and Z's in it, cool, totally allowed. Wait, I'm sorry, I got my wires crossed. Okay, totally will. Okay, pretend that I didn't just say that. I'm sorry. There will be no dependence on Y and Z because this is an outside bound, not an inside bound. Does everybody see what I did wrong there? Okay, so we're going to solve for a value that has no dependence on any other variables. Is everybody happy with that? Again, sorry for the momentary screw up there. Okay, so we solved for X. There it is. Everybody happy with the process? Okay, let's proceed. Now again, the picture is really important. We've got our X bounds worked out. We're going to fix a value of X. We're now interested only in this X slice. Let's think now about the range of values of Y. What do Y slices look like? Well, here's a generic Y slice. Again, we're taking a slice perpendicular to the Y-axis of our existing slice perpendicular to the X-axis. Okay, so we think about first and last. The first one is a slice that's here, which is obviously in the plane y equals 0. So again, freebies. Again, go ahead. If you get lucky, all good. Okay. So next, though, the last y slice. is this. Let's think very carefully. What do we know about that point? By the way, don't worry about that over there. Common mistake, very common mistake. Students will say, well, the largest value of y is this point way over here. So shouldn't it be y equals 1? We are not interested in the largest value of y on the solid. We are interested in the largest value of y on our x slice. This point over here will get accounted for. It'll get accounted for by a different x slice, right? So let's see if I can draw. So maybe about like that. That x slice will get this point. Fear not. It's all good, right? But we're interested in how the y bounds depend on x. So again, we are focused on just the x slice. And the upper bound for y there is that point right there. Good? Okay, so what do we know? Well, the first thing that we know about this point is it's on our x slice. Now, this is a little crutch that I like. You don't have to do this. I find this a good, I don't know, reminder or something. I find this satisfying. I just like to write down x equals x. That doesn't mean anything. That's obvious. Of course it is, right? This is my little reminder to myself that x is allowed to be whatever. I mean, my answer is going to be in terms of x. X remains a variable. We're not going to be solving for x. We're going to be solving for stuff in terms of x. So that's, again, my little personal reminder. Totally optional. You don't have to do it. But what else I know about this point? Well, I can see from the picture, thank you, picture, it's in that plane z equals 0. I can also see from the picture, thank you, picture, it is in this plane that has that equation right there. Is that cool? Wait, what are we doing here again? Oh, yeah, that's right. I'm trying to find an upper y bound. So in all of this algebra right here, I need to solve for y. And this is where what I said before actually is true. This is a function of one of the other variables. You solve for y here, and the best you can do is to get that y is this function of x. It's allowed to be a function of x because x is further to the outside. All good. And then this is our upper bound for y. Everybody happy? Okay. All right, and then quickly through the last one. X and y both fixed. Oh, let's see here. I guess I'll use blue. X and y both fixed. Think about a point down there in the xy plane, sort of, as it were. This is the slice of the slice. We think about first and last values of z. The first value of z is there. It's obviously in the plane z equals 0. So again, sometimes you get lucky and everything's good. So convenient. You won't always get that lucky, to be clear. Right? Very often it's not. This is just a convenient first example. But we did get lucky there. And then the last value of z is going to come from that point. And what do I know about that point? Well, I already know x and y, for one thing. What else do I know about that point? Well, it's on, let's see here, color choices. It's on this plane. Thank you, picture. Is that cool? Okay. Let's see, what are we doing again? That's right, that we're solving for z. So I'm going to solve for z in this equation. Best I can do is this, and that is my z upper bound. Function of x and y as it's allowed to be, because x and y are further to the outside. Everybody's good? Okay, so that's the mechanics of the process. Everything that follows is basically examples and strategy. Yeah, try to choose your between the 6 orders. Try to choose wisely, best you can. There is no perfect algorithm to tell you which of the 6 orders you should choose. Just like with double integrals, try not to slice through corners. Again, bad things happen. It means you're going to have to write down multiple iterated integrals. That's no fun. Okay. Again, this isn't always true, but if in some meaningful sense, if you really have a significant algebraic preference to have one of the variables be a function of the other 2, put it on the inside, where that is in fact what you will be solving for as a function of the other 2. Right? So just try not to paint yourself into some sort of weird algebraic corner in a way that's easily avoidable. Okay. The last little point of strategy here is hard to understand until you see an example. So I'm going to momentarily skip this, come back to this after we sort of encounter it in the wild here, if we will, momentarily. So here's my next example. By the way, a really hard diagram to draw. If you don't believe me, give it a try. Right? It's a tricky one. This exact figure is one of the figures that's in my one of my recordings on the YouTube channel for how to draw, mathematical drawing. And there are lots of little considerations and points that go into making this the acceptable right figure that it is. I'm not saying this is a great figure, right? Some sort of computer generated thing would probably be better, but this is something you can do with a pencil, right? This is low tech. This is always accessible, and so if you'd like to know exactly what was I thinking, exactly how did I, all the little subtleties of how every single pen stroke here was decided upon, go watch those videos. All right. Okay. So, what do we got here? We have z equals 1, which is a plane up here like this. We have, colors. We have this paraboloid. Y'all recall paraboloids, which this is one of. And the part in the first octant means that we're just looking at this part of it. We're not looking at the part to the left of the xz plane and the part behind the yz plane. That is first octant. Okay, everybody see the solid here? Okay. Now, what order are we going to slice? Here's the very first thing I notice. Right? I don't even need the picture for that. I see right there that, look, you give me my choice. I don't want to solve for x as a function of y and z. It's not that I can't do it, but I don't like square roots. And I don't like it when square roots get into my inside bounds, because then square roots will get into my eventual integrands, and square roots and integrands are a huge negative. Right? So I think this right here is pretty good motivation to put dz on the inside, because that's the one that I want to be solving for, because that's the one that is most easily a function of the other 2. Is that cool? Okay. All right, well, now that means that I'm going to have dx and dz on the outside. So here begins our discussion about good projections. This is what we skipped up here. What is a good projection? So I'm just going to walk through kind of how this works out in this case. And this is a good metaphor for what's kind of, I'm not going to say always, but whenever you have a good projection, it's going to be kind of analogous to this. So the shadow. Right? If I were to say, let's look at the xy, because dx and dy are our outside bounds. Let's look at this shadow. Shadow's a quarter disk. That's not that bad. I could deal with it, right? Why do I care? What gives? What's the purpose of looking at this shadow? And here's the wonderful little argument. As you slice up your solid, you are effectively also slicing up the shadow. Every time you take a slice of your solid, you're taking a slice of your shadow as well. The starting slice of your solid is going to have the same value of y as the starting slice of your shadow. All the slicing that you do of the solid is when you're only looking in the x and y directions, well, the shadow has all of the same x and y coordinates as the solid. So this is the big win. The big reason that we care about this idea of looking at a projection, which again is just kind of a fancy way of saying the shadow down here, is it's now a two-dimensional picture that I can think about instead of this much more geometrically challenging, much more artistically challenging three-dimensional solid. I can just look at the shadow. It's a two-dimensional picture, much easier to deal with geometrically and artistically. This is a big win, right? So phooey on all the stuff up here. I don't need to worry about that at all, other than as a tool for helping me understand the shadow. There's the shadow, and you could just use good old regular old double integral methods to slice up this domain to get your y bounds and then your x bounds. And I'm going to leave those details as an exercise for y'all. Y'all have done stuff like that before. It's no big deal. Right? You got to think about the equations of the curves and the slices and the blah, blah, blah. So make sure you can do that. Right? The two-dimensional little analysis there. Yeah?
Does not be just one with a level of vision.
I'm sorry, say again?
We're only in one quadrant.
Absolutely not. No, that's a common misconception. Yeah, so if we were interested in computing the volume, then that would be true. We are not interested in computing the volume. We're computing. So you keep in mind, this is an accumulating quantity, right? So I think kind of what happened there, and I don't know, and it doesn't matter. It may be that you were thinking in terms of a volume as would be represented by computing with a double integral, right? So it's easy to make that conflation. I'm just going to point that out for whatever that might be worth. See how easy it is to make that mistake. But yeah, no, we're not interested in the volume here. We're interested in computing some double integral. I don't know what f is. It could be anything, right? But we're interested in computing something along the lines of the amount of mass in here or something like that. Does that make sense?
Yeah.
Yeah. Cool. Okay. All righty. By the way, I'm just going to make another observation about that. Just from a strategic point of view, if you make an argument to turn one problem into another problem, which mathematicians do all the time, I'm all for it. There's always a pro-con. Right? The pro is, hey, I get to this new question that I write down might be a little bit easier. The con, ever-present con, my argument might have a mistake in it that I haven't noticed yet. So I would suggest, don't make any argument if you're not clear on what you gain. Right? So let's look at this and let's compare, doing this question on this shape as opposed to doing the question on the which you might call the whole, right? The all four pieces together. Would that make it an easier problem? I'm not clear that it's easier. I'm not clear what we gain out of that. Does that make sense? Yeah. So unnecessary arguments, a little risky. Right? You're taking on a little risk that it might not be right, and for no apparent gain, you probably shouldn't do it. Okay. All right. Okay. So now we've got our x and y bounds. Let's fix a value of x and y. So we'll be looking at a point like that. Let's say. Let's see here. I'm going to try to get all this onto the same page. If I can. There we go. Here's going to be our slice in the z direction. And again, first and last and all that. Now, one thing that I'm going to point out that worked out really nicely in this example, and this is another thing you should always check for when you're thinking about making a projection argument like we just did. How am I going to find this lower bound for z? What surface is it going to be on? And here's the good news. It's always on this same surface. No matter which x and y we're looking at, the lower bound for z is always on the same surface. So I'm going to come back up to here and point out that the bottom surface is consistent. It's always the same bottom surface. And it's not algebraically undesirable. Okay. Likewise, now let's look at the top point. You know, the last value of z. Well, that top point is always on this surface, and it's always consistently on the same surface with the same equation, no matter which x and y you pick. All right, so this is what I meant up here by you want your top and bottom surfaces to be consistent, is this right here. And again, in this case, yeah, absolutely. Bottom is always the orange surface, the top is always that purple surface. Okay. And then a little algebra, not much to it. You want to solve for z in, let's see, for the bottom surface. Well, there's z. It's easy to solve for, and it's that. You want to get your upper bound. You solve for z on the top surface. Again, easy to solve for. And that gives you that. Okay. So I think that's a really nice way to do. You'd be surprised how often this comes up, that we get good projections. This is a powerful strategy. This is an underappreciated strategy. It avoids us drawing difficult pictures with difficult slices. And let's just, for fun, let's just think through how hard would this problem have been had we not made this projection argument. And well, I would have had to think about and successfully draw what that y slice looks like. I'd have to think about that y slice, think about and draw what its slices look like, and it gets hard, just if only artistically. Okay. Here's another example. Suppose your domain is the unit ball, and just cause, no particular reason, let's suppose we're doing our slicing in that order. Now again, you can start slicing it up, and that's kind of what I have drawn here. Our x slices, let's see, let me do it like that. Our x slices are all going to be kind of discs. Right? Now, there's a geometric appeal. If you have a solid ball, you take a slice perpendicular to the x-axis, it's going to be a disc. First and last in geometry games, etc. Given such a disk, the z slices perpendicular to the z-axis, little strips like that, little line segments like so. And you can think about first and last there, and this, I mean, it does start to get pretty challenging because, how do you draw and how do you figure that point and that y coordinate? This is harder than it looks. I went to a lot of trouble to make a drawing that's not horrible. It's not good, but it's not horrible. And again, making a not horrible drawing here, pretty tricky. Et cetera, et cetera. So you can think through all this from a slicing point of view. Here's what I think is much easier in this case. Doesn't always work. Let's think about the XZ projection. What is the shadow? If I ignore all the y coordinates, if I just smush everything into the XZ plane, what does that look like? And, well, I think it's pretty easy to argue that's just a disk not great art, but it doesn't need to be because I'm portraying a pretty simple geometric appeal here. And I know how to slice up a disk. This is a double integral argument. Good to make sure you can go through these details, but if you have, again, looking at the picture, right, it's the unit disk in the XZ plane, and if you slice that up in this order, these are your bounds. Two-dimensional picture, two-dimensional argument, not geometrically challenging, not artistically challenging. Okay? We're 2/3 of the way done. And the last thing we have to do is just think about the top and bottom surfaces, by which I mean, okay, looking at y on one of these y slices, so kind of like so. Well, I should call that a z slice of an x slice. As I go in the y direction, though, the first point is right there. That's a point on the unit on the unit sphere. The unit sphere has an easy equation that I can write down. Right? And I can then solve for y. I got to remind myself I'm interested in y, so I solve for y. Clearly interested in the negative value of y. And when you solve for y, you get that. Yeah?
What's the difference between a unit ball and a unit sphere?
A ball is a three-dimensional solid, and a sphere is just the two-dimensional surface. Yeah. Yeah, that's right. So a sphere is the surface that is the boundary of the ball. Yeah, that's right. It's likewise, a circle is the boundary curve for a disk. And it's just lingo, but we need to make those distinctions. Okay, good place to draw the line. See y'all later, and again, welcome back. Don't forget about attendance.